Hey there, educator, and welcome back to the Make Math Happen podcast. I'm your host, Lanisha, and today we're talking about how can we help students make sense of transformations and symmetry. Last week, we talked about how geometry is the visual foundation of mathematics and why starting the year with geometry really matters. Today, we're going to zoom in on one of the most powerful and most misunderstood aspects of geometry, and that's movement. I want you to think about angles, lines, transformations. These are all ideas that are everywhere in the K 8 standards. Yet by the time students reach middle school, many of them still feel disconnected and procedural. So, my goal today is to help us rethink how these ideas develop over time and what students need long before we ever introduce coordinate rules. So, first things first, movement starts early, even if we don't call it that. When students first encounter geometry in the early grades, they're not learning formal vocabulary. They're learning how shapes behave. In kindergarten and first grade, students describe positions using language like above, below, beside, and next to. They identify shapes regardless of orientation and size. They build, they draw, and compose shapes using physical materials. All of that work is about movement and relationship, even if the standards don't yet use words like rotation and reflection. By second and third grade, students begin composing and decomposing shapes and reasoning about attributes. They're learning that shapes can change position without changing identity. That idea is critical. A square is still a square when you turn it. A triangle is still a triangle when you flip it. Those experiences are the earliest seeds of transformation thinking. By fourth grade, students formally study angles. They learn to measure them, compare them, and reason about how angles are formed by intersecting lines. But here's where things often start to shift in the wrong direction. We move too quickly to tools and procedures, protractors, degrees, numbers. What students really need first is to understand that angles describe turning and position. They need to see angles as relationships between lines, not just numbers on a tool. If students don't understand that two intersecting lines create angle relationships, then ideas like vertical angles, supplementary angles, and corresponding angles will always feel like disconnected rules instead of predictable outcomes. The standards expect students to reason about these relationships well before they formalize them. That reasoning is what allows them to predict, not memorize. When we talk about transformations, there are three core types students encounter across the grades. They have translations where they're sliding figures, reflections where they're flipping figures, and rotations where they're turning figures. What's important is that students experience these transformations physically and visually before they ever describe them algebraically or on a coordinate plane. In middle school, especially in seventh and eighth grade, students are expected to describe transformations precisely and analyze their effects. But those expectations assume students already understand one key idea. Movement does not change shape, size, or angle measure. If students don't internalize that idea early, they struggle later. I see it quite often in the eighth grade classrooms where we're working in that rigid transformation unit and students are struggling. I just mentioned how we're talking about angles in the fourth grade. So, seventh grade is not the very first time. They've had that experience in fourth grade. The challenge is students aren't doing a lot with angles in fifth and sixth grade. So, with those 2 years where we're not spending as much time talking about those concepts, we know that students can forget things, right? So, that's why it's super important for us to review previous content, to review previous learning, to make sure that we are able to activate that prior knowledge, right? Help them pull that from memory if it's there and giving them those authentic experiences where they can make sense of things. Because again, I've been in classrooms where the teachers or maybe even myself was teaching their heart out about angles and you could ask a student to point to an angle and they would have no idea where to point. You could see the wheels turning in their head as they're trying to figure out what is she expecting me to do right now? Because I really don't understand, but I don't want to say I don't understand because I really want her to continue so I can get this class over with. Yeah, that's pretty much what's happening in kids' heads. But I share that to say that oftentimes we are up there teaching and the students have no idea what we're talking about because they're missing key pieces. So it's hard for me to talk about vertical angles and supplementary angles and adjacent angles and all these other types of angles if I don't even know what an angle is. I don't even know what an angle is. and you are expecting me to find the measure of an angle? You're expecting me to use expressions and solve for the value of unknown variables that are used to describe the angle's measure? That's a lot, teacher. You're asking for a lot. Okay, so symmetry is one of the most powerful connectors in geometry. Students encounter symmetry formally in fourth grade, but the intuition behind it develops much earlier. Symmetry helps students reason about balance, equivalence, and invariance. When a shape is reflected across a line of symmetry, parts match, distances remain equal, angles remain congruent. This idea becomes essential later when students study transformations in the coordinate plane and when they begin connecting geometry to functions. If students can see that symmetry preserves structure, they're better prepared to understand why certain relationships stay consistent even as representations change. You guys know I'm always talking about the various connections across domains. So, sharing this with you really just makes me feel good because people often say geometry is not my strong suit. Geometry is not my favorite. I struggle with geometry, not understanding that geometry is such a critical part of all the other domains. It's really connected. So I don't want us to look at geometry as something that is difficult or challenging just because we're working with space. I want us to use that as an opportunity to learn more, to do some research, to do some studying, to push ourselves to become more well versed in the connections between geometry and all the other domains. So I want to be honest about a common stumbling block that we create. Many of the struggles that students have with transformations are instructional, they're not cognitive. We often introduce vocabulary before students have an opportunity to experience the concept. We often jump to coordinate rules way too quickly. And I cannot say this enough. Just because we, as a teacher, may have learned the rule and the rule was super helpful for us to figure these transformations out or to answer these questions or to do whatever it is that we needed to do with those rules, just because it was helpful for us does not mean that it's going to be helpful for the students who are in our classrooms. So I need for us as teachers to step outside of our own experiences and maybe try to see the learning through our students' eyes. It's important that we do that because only then will we realize that just because something feels easy to you, just because something worked for you, does not mean that it's easy or it's going to work for anyone else. If I'm ever in a teacher's classroom when they're in their transformation unit, I'll always take a piece of paper. Sometimes I'll even take a pencil and we'll talk about 90-degree turns. And I'll show them the piece of paper. I'll have them to identify what they would consider the base and the height or the length and the width of the paper. I'll turn it 90 degrees and then I'll ask them what was the effect? What happened? Okay, what happened there? Well, it looked like the base became the height and the height became the base. And then I'll use that to connect to the ordered pair. And then eventually, once they've had a lot of experience with it, then we can connect it to the rules. But first, I need you to make sense of it. I need for a light bulb to go off in your mind. I need for it to be like, oh, before I give you a rule to memorize when I know memorization is the eventual goal, but that's not where we're starting. We're starting by making sense of things. We're starting with the reasoning. And then once we get the reasoning, once it makes sense, then we can commit things to memory. Okay. So another thing that we often do is we teach transformations as isolated procedures. I want you to think about multiplication facts and how oftentimes we want to quiz kids. We want them to memorize all of these multiplication facts, but we're not emphasizing the property, the commutative property that is very present, right? And if students understood the relationships between the multiplication facts or the times table, then they would recognize that there aren't that many facts for them to memorize, for them to know, right? Once they start looking at that relationship between 6 times 7 and 7 times 6, or 2 times 3 and 3 times 2, now I don't have as many. This is what I want you to think about when I say teach transformations as isolated procedures. We have to connect things because through the connection is the reduction in the cognitive load. Okay. So the next thing that we often do is rely on static images instead of movement. So I know that physical manipulatives, we don't really want to do them as much because, sometimes our kids are not as responsible and things get lost or things get broken. Well, there are applets that we can use that can also show students' movements. When I use the resource, what I realize is those applets are really good resources or really good tools for us to use for students to see what is happening when we rotate, right? Because if I'm just looking at a piece of paper, sure, I can use patty paper and I can rotate that patty paper and I can really make sense of that. And I can also use that applet as well. So there's a lot of things out there that we can use that can bring things to life so that we're not relying on static images and hoping that students can see it happening in their mind, hoping that students can connect this static non-moving image to what we want them to see and understand about movement. Then students try to memorize instead of reason. This is huge. We're wanting students to memorize instead of reason. A small shift makes a big difference. Instead of asking, what rule do we use? Ask, what happened to the shape? Instead of saying, reflect over the y axis, which parts stayed the same and which parts moved? Instead of starting with graph paper, start with tracing paper, that patty paper I mentioned earlier. Start with mirrors or motion. Language matters, questions also matter. This is not just about geometry. When students understand movement and transformation, they're better prepared for proportional reasoning because they understand scale and invariance. They're better prepared for equations because they see balance and structure. They're better prepared for functions because they can visualize change over time. In eighth grade, transformation set the stage for connecting dilations to slope and translations to linear relationships. Movement becomes meaning. This is why geometry cannot be rushed or treated as a side unit. It's rehearsal for everything that comes next. So, whether you're teaching a class of 30 students or supporting one child at home, here are a few simple ways to strengthen transformation thinking. Use physical movement, turn papers, flip shapes, rotate objects. Ask prediction questions before measuring or calculating. Emphasize what stays the same during movement. Delay formal rules until students can describe the movement in their own words. These small choices build intuition, and intuition is what students rely on when the math gets more challenging, when it gets harder. Geometry becomes powerful when students can see it move. Angles, lines, and transformations are not just standards to cover, they're opportunities to help students reason, predict, and connect ideas across mathematics. In the next episode, we'll take this visual reasoning and apply it directly to area, surface area, and volume, where many students struggle the most, where these foundations matter deeply. Until then, keep looking for the movement. That's where understanding begins. I'll see you guys in the next episode.